Okay, welcome to Intervals of Convergence, Part 2, wherein we actually discuss intervals of convergence. Before we do, though, let's just remember, what does it mean to say interval of convergence? Here you see the sine x function, and this line is the linearization for the sine x function. In other words, it's the Maclaurin series, but only evaluated at one term, and that's this right here. So as I drag this slider, I'm going to add more and more terms of the Maclaurin series. And as I add more and more terms, you see that a larger interval of x values seems to be equal to the sine x function. And it seems like the more terms that I add, the wider that interval becomes. That's because the Taylor series, or the Maclaurin series, for the sine x function converges on the interval of all real numbers. So that's just another way of saying that this function is the same as the sine x function over all real numbers if you evaluate it to all of the terms. But it's not that way for every single Taylor series. Here's a different Taylor series. Oops, that was secret. So in blue here, you see a function. And then in orange or red, you see, again, the first term of the Taylor series for that function. And it's the same thing. As I add more terms here, it looks like you can see these x values are equal to the function. But unlike sine, as I added more values, the interval of x values for which the Taylor series equals the function got larger and larger. And here, it doesn't seem to be getting larger and larger. Here, we seem to be just between -1 and +1. So the interval of convergence for this Taylor series is from -1 to +1. We'd say that the radius of convergence was 1. For sine, the interval of convergence is all real numbers. So in summary, interval of convergence just means the domain of x values for which the Taylor series equals the original function it's supposed to represent. Okay, with that in mind, let's work some problems.